Hello and welcome to this session. In this session, we will talk about the Fourier transforms. Fourier transform. So what is a Fourier transform? Fourier transform is a mathematical tool usually used to convert a function or a signal from its time domain or sometimes from the spatial domain into its frequency domain or vice versa. So Fourier transform decomposes complex signals into a combination of sine or cosine waves of various frequencies. The time domain here represents how a signal changes over time, while the frequency domain shows the contribution of different frequencies in the signal. Fourier transforms has many uses, and just to highlight a few, for example, it can be used in image processing, either to enhance or to compress images, for example, the JPEG format. So when compressing an image, like in the case of the JPEG format, Fourier transforms help convert image from the spatial domain. And in the spatial domain, we usually see the pixels. And Fourier transform converts this into a frequency domain. In the frequency domain, low frequency components, which usually represent the broad or important features of the image, are prioritized, while the high frequency components, these are the fine details of the image or even the noise, are discarded or they are reduced, and this serves to save the storage space. The benefit of this is that by focusing on essential frequencies, the Fourier-based techniques reduce the size of a file without significantly reducing the image quality. And this is why the JPEG formats are compact and yet they are visually acceptable in most of the applications. In the case of the enhancement of the image, Fourier transform helps to apply filters in the frequency domain, such as sharpening or enhancing details, or even the noise reduction. So these filters will usually target some specific frequency ranges to improve the image quality without affecting the entire image quality. Now, some other applications on, for example, in medical, such as the CT scans and MRI. So, Fourier transforms are usually used in CT scans and MRI. So, in CT scans and MRI, data is collected in a form which is not immediately interpretable as an image. So it is collected as projections or raw frequency data. Fourier transforms will help process this data to reconstruct clear and detailed image of the internal body structure. In CT scans, for example, the scanner collects X-ray projections from multiple angles around the patient. A mathematical process, including the Fourier transform, then combines these projections to reconstruct a cross-sectional slices of the body. MRIs, on the other hand, detect changes in magnetic resonance signals from the body. The frequency information is transformed into spatial information using Fourier transform, and this produces high resolution images of soft tissues. Now, these reconstructions will then allow doctors to detect and diagnose conditions such as tumors, fractures, or abnormalities with very high precision. So we want to look at exactly what this kind of mathematical functions and how we can compute the Fourier transforms for some given function. Now, but before we go into the Fourier transform, we define what we mean by absolutely integrable function. Absolutely integrable function. So what is an absolutely integrable function? Now, a function f of t, suppose we have a function f of t, we shall say that this function is absolutely integrable if the integral from minus infinity to positive infinity of this function, f of t, the absolute value, is finite, provided that this integral is finite, that is less than infinity. Then we say that a function f of t is absolutely integrable. An example of an absolutely integrable function, if you are given a function f of t is equals to x raised to power minus 2 alpha 3 for x between 0 and 1, and the function is 0 elsewhere. This is f of x here. So this function is absolutely integrable. And to verify this, we can simply work out the integral from negative infinity to infinity of f of x dx. In this case, we have the integral from 0 to 1, x raised to power minus 2 alpha 3 dx. Remember, this function is 0 at all other points except between 0 and 1. So when we work out this integral, if we work out this integral, we get this is equals to 3 x raised to power 1 alpha 3, and the limits are from 0 to 1. So that when we put the limits, this will be 3 1 raised to power 1 over 3 minus 0, which is equals to 3. And you see this is finite. So the function is absolutely integrable. The function is absolutely integrable. There may be other functions which may not be absolutely integrable. For example, if we write a function similar to the one we have there, but we have now x raised to power minus 2 alpha 3 for x greater than 1 and 0 elsewhere. So this function is not absolutely integrable. And we can verify this. We need to work out the integral from minus infinity to infinity of f of x dx. So in this case, when we start from minus infinity all the way up to 1, see that when we write this, if we write the integral from minus infinity all the way up to 1, in this section the function is 0. And then we have the integral from 1 to infinity, where the function is x raised to power 2 over 3, minus 2 over 3 in this case. So if we work out, we say that this integral will be 0, because we are integrating 0, and that's a definite integral. So that we get, when we integrate the second integral here, we get 3, x raised to power 1 over 3, and x increases from 0 to infinity. So that this will be 3 multiplying the limit as x approaches infinity of x raised to power 1 over 3 minus 0. And if we work out this limit here, you'll get infinity. The cube root of infinity is infinity. So that this integral is infinite. And so the function is not absolutely integrable. So now, the reason why we needed to define the absolutely integrable function is because the Fourier transform is defined for only functions which are absolutely integrable. So when we talk about the Fourier transform, we require that the function be absolutely integrable. So if we have a function f of t which is absolutely integrable, then we can define its Fourier transform. So if f of t is a function which is absolutely integrable, then its Fourier transform exists. We usually denote this Fourier transform of f of t by this. A simpler notation is f hat omega, and this is defined by 1 over the square root of 2 pi, the integral from minus infinity to infinity, e raised to power negative I omega t times f of t dt. So e raised to power negative I omega t is the kernel of the transformation. I is the imaginary unit, and omega is the frequency, usually a parameter in this integration. So this is the definition of the Fourier transform. So t represents time. Omega is the frequency, which is the inverse of time. Now, under suitable conditions, f of t can be reconstructed when we have the Fourier transform. The Fourier transform, we shall use this notation to denote the Fourier transform of f of t. So if f hat omega is given, then under suitable conditions it is possible to reconstruct f of t, the time domain, using what we call the Fourier inversion formula. So the Fourier inversion formula is similar to the Fourier transform formula itself. So we write f of t is 1 divided by the square root of 2 pi, integral from minus infinity to infinity, e raised to power I omega t times f hat omega. Then we integrate with respect to omega. Notice that the kernel of the, not the kernel of the transformation, e raised to power I omega t. There is no negative here, as we had here. So that's the difference. Then we have the function f of t. Here we have its transform. Then we are integrating with respect to omega. So this formula here, we call it the Fourier inversion formula. Call it the Fourier inversion formula. So it is important to remember that the Fourier transform exists whenever f of t is absolutely integrable. And to say that f of t is absolutely integrable means that the integral from minus infinity to infinity of f of t dt is finite. Is finite. So let's do an example. Suppose you are given a function f of t defined as 1 in the interval between -2 to +2, and it is 0 elsewhere. And we want to find the Fourier transform of this function. We want to find the Fourier transform of this function. Notice that this function is a constant function between -2 and 2. It has a value 1, and at all the other points, the function has the value 0. So when we write its Fourier transform, then by definition, we have 1 over the square root of 2 pi integral from minus infinity to positive infinity f of t e raised to power negative I omega t. Then we integrate with respect to t. Notice that the function is 0 in all sections except between t is -2 and +2, where it is 1. So when working out this integral, therefore, because we are saying that between -2 and +2, f of t here is equals to 1. But at any other point, f of t is equals to 0. F of t is equals to 0. At all other sections, the only section where the function is non-zero is this section here, between -2 and 2. So when we're working out this integral, where the function is 0, we integrate 0 to get 0. So we concentrate on this section where the function is non-zero. So we shall write 1 over the square root of 2 pi integral from -2 to +2 e raised to power negative I omega t dt. Notice that f of t is 1, so we just have 1 times this, which is the same. So we get 1 over the square root of 2 pi. Then we have -1 all over I omega e raised to power negative I omega t. T increases from -2 to +2. So this will give us 1 divided by the square root of 2 pi times -1 all over I omega. Then we have e raised to power negative 2 omega t, minus e raised to power 2 omega t. So this is the Fourier transform of that function. We can simplify this by writing. Notice that it is possible to multiply here by 2 and divide by 2. It is possible to multiply this by 2 and divide the same by 2, so that we have 2 all over 2 root 2 pi. This will be minus. Sorry, let me push the negative somewhere. Then we have 1 all over I omega Then I can interchange these two terms, then multiply them by -1, each by -1, so that we have e raised to power 2 omega t minus e raised to power 2 omega t minus, so that this can be reduced to the square root of 2 divided by pi times 1 over omega, then e raised to power 2 omega. I think something is not correct here. 2 omega. I think something is not correct here. This should have been I, not T. Should have been I here, because we replaced T with 2 and minus 2. So we get 2 omega I, not 2 omega T. So this is 2 omega I. So this we get 2 omega I minus 2, e raised to power minus 2 omega I divided by 2I. So we have the 2I, 2 here. In this section, we have 2 and I. Now the quantity, this function here inside the brackets is the same as the sine 2 omega. So we write 2 over pi. Then we have sine of 2 omega divided by omega. So this is just simplification. Otherwise, we could have stopped at this point. So we can do a second example. So suppose we have a function f of t defined as e raised to power negative t for t positive and 0 when t is negative. So we want to find the Fourier transform of this. So we write the definition. 1 divided by the square root of 2 pi, the integral from minus infinity to infinity, e raised to power negative I omega t, f of t, dt. Now, when applying this formula to this function, notice that for t, when t is negative, the function f of t is 0. So we shall concentrate on the section where the function is non-zero. That is for t greater than 0. So in this case, we write 1 divided by the square root of 2 pi, integral from 0 to infinity, e raised to power negative I omega t times e raised to power negative t dt. Working out this, we can simplify 1 over the square root of 2 pi. Then we have integral from 0 to infinity. Notice that we can apply the rows of indices here, so that we write e raised to power negative 1 plus I omega, then t dt. Integrating this, we get minus 1 all over 1 plus I omega, then e raised to power negative 1 plus I omega t, then t increases from 0 to infinity. So that when we put the limits, we get this, minus 1 all over 1 plus I omega. When t goes to infinity, notice that this is e raised to power negative. The power is negative, so when t goes to infinity, this quantity becomes very small. It will approach, the limit will be approaching 0. Then when t is 0, e raised to power 0 is 1. So that the result we get 1 over the square root of 2 pi 1 divided by 1 plus I omega, which is the Fourier transform of the given function. The given function was f of t was e raised to power negative t when t is positive and 0 elsewhere. So basically, this is how you can get the Fourier transform of various functions. You just need to write the formula first. Write the formula first. Write the formula first. Then substitute the function. Then choose a suitable integration method and work out. Then simplify where necessary. So that is basically what how we can find the Fourier transforms of different functions. And in the next session, we shall talk about the Fourier transforms of odd and even functions. So thank you for watching and enjoy your time.